Hello and welcome, fellow stargazer. Tonight, under the quiet canopy of the cosmos, we're going to gently explore a question that has fascinated astronomers and dreamers alike. Why do planets spin? Spinning worlds, drifting through space like dancers in the dark. What set them in motion? Why do some spin quickly while others barely turn at all? As we drift deeper into this soothing story, let us know in the comments. Where in the world are you watching from tonight? Whether you're nestled beneath northern skies or surrounded by the sounds of a warm southern evening, we're glad you're here. Now, let's begin our celestial journey. Before there were planets, there was silence. At least the kind of silence we imagine in the void before time took shape, before the stars had even begun to shine. In the beginning, there was only a vast, cold cloud. A soft swirl of gas and dust, so delicate and thin that it would have seemed invisible, even if you could somehow stand there and look. These clouds, known as nebulae, drifted slowly through the emptiness of space. Remnants of earlier stars that had lived, burned brightly, and then died in great explosions called supernovae. The ashes of these ancient stars became the seeds of new worlds. But even in this quiet, the universe was never still. Motion is stitched into the fabric of everything, subtle, eternal. This great cosmic cloud wasn't just floating, it was gently spinning, almost imperceptibly. Even the tiniest nudge of movement mattered, because in the empty, frictionless void of space, motion is preserved. There is nothing to slow it down, no air, no wind, no surface to stop against. If something starts spinning in space, it keeps spinning, forever. Over time, this peaceful cloud began to feel the pull of gravity. Each particle of dust, each molecule of gas, felt the attraction of all the others. Slowly, irresistibly, the cloud began to collapse inward, its center pulling more and more material toward it. And as it collapsed, something beautiful happened. The cloud began to spin faster. This might seem strange, but you've seen this before, maybe without even realizing it. Think of a figure skater, arms outstretched, gently turning on the ice. Now picture her pulling her arms in tight. What happens? She spins faster. It's a simple law of physics. When something spinning becomes more compact, it speeds up. This is called the conservation of angular momentum, and the same law governed the birth of our solar system. As the vast cloud collapsed under its own gravity, it spun faster and faster, flattening into a wide, thin disk, a swirling, spiraling pancake of dust and gas. In the center of that disk, something incredible was happening. Pressures and temperatures rose to extraordinary levels, and in time, the first spark of nuclear fusion ignited. A star was born, our sun. But our story tonight isn't just about the sun, it's about the leftovers. The tiny fragments and grains of dust that remained in the spinning disk around the newborn star. These grains began to stick together, little by little, drawn to each other by the same invisible hand of gravity. Clumps formed, then larger bodies, and eventually, after millions of years, these became the planets. Each of these new worlds inherited the spin of the original cloud. That soft, ancient rotation lived on in the way planets turned. Not perfectly, of course. Collisions, uneven mass distributions, and the whims of gravity added their own twists and turns. But the basic truth remained. Planets spin because the cloud they were born from spun too. So when you look up at the night sky and think about Earth spinning gently beneath you, or imagine Jupiter with its colossal storms and rapid rotation, know this: their movement began long before they were planets. It began in silence, in a cloud no one saw, under laws written into the bones of the universe. And still it turns. Long before Earth had oceans, forests, or even a name, and long before the sun blazed bright in the sky, there existed something far more ancient. a vast and delicate swirl of gas and dust drifting through the Milky Way. This was a nebula, a giant, gentle cloud composed mostly of hydrogen and helium, the simplest and oldest elements in the universe. Scattered throughout this soft haze were trace amounts of heavier elements, carbon, oxygen, iron, left behind by older stars that had lived out their lifespans and died in magnificent supernova. Their deaths enriched the universe with the raw materials needed to create new stars, new planets, and eventually, life itself. This cloud may have seemed still, suspended in the dark, like a breath held in space. But if you could zoom in, across light years and eons, you would see it was not motionless. There was a subtle turning, a faint rotation. Not in the way a wheel spins or a top twirls, but like a slow, ancient dance. Some parts drifted one way, others drifted slightly another. But on the whole, the entire cloud possessed a quiet spin, a leftover from gravitational interactions, galactic tides, and the long, invisible hands of cosmic history. This spin, however faint, held a secret power. In the emptiness of space, nothing gets in the way. There's no atmosphere to slow things down, no resistance to sap energy from movement. So even a tiny, almost unnoticeable rotation can become significant over time. That's one of the mysteries of the universe. Even the smallest things can grow if given time and space. Eventually, this seemingly tranquil cloud was disturbed. Perhaps it passed near another star, or maybe it encountered shock waves from a nearby supernova. Whatever the cause, the cloud began to collapse. Gravity took over. Like a slow inhale, the center of the cloud started pulling the outer layers toward it. It didn't happen quickly, not in human terms. It took millions of years. But gravity is patient. It never stops pulling. And as the cloud collapsed, that gentle spin became more noticeable. The same physical principle that makes figure skaters spin faster when they pull in their arms now took over on a cosmic scale. The cloud, now denser at its core, began to spin faster and faster. Its shape started to change. Instead of remaining a loosely scattered cloud, it flattened into a disk, wide, thin, and spiraling. This is the protoplanetary disk, the birthplace of stars and planets alike. Within this disk, particles began to collide. Microscopic grains of dust bumped into each other, at first gently, like snowflakes touching, and then with increasing speed and frequency. Many of these collisions caused the particles to stick together. Electrostatic forces helped them cling, like tiny magnets in space. Over time, these specks grew into pebbles, then into rocks, then into mountain-sized chunks of matter known as planetesimals. And all throughout this process, the spin continued. It was no longer just the cloud spinning. Now, each forming body carried its own piece of the spin, its own rotation, inherited from the swirling disk in which it was born. Some rotated rapidly, others more slowly, but none were still. Even as they grew, crashed, and coalesced, that initial motion persisted. What began as a quiet swirl of gas, a motion so faint it would have been impossible to detect, became the force that shaped entire worlds. It is astonishing to consider that the reason Earth spins, the reason day turns into night, and the stars appear to march across our sky, is because of that ancient, ghostly rotation in a cloud that no longer exists. The spinning nebula is gone now, long absorbed into the star and planets it created. But its legacy endures. Every time you watch the sunrise, every time you gaze up at the stars slowly drifting overhead, you're witnessing the echoes of that original motion. The universe remembers everything, and in the way planets turn, it still remembers the dance of the spinning nebula. And so, quietly, persistently, the planets continue to spin, cradled in motion born from silence. Gravity is often thought of as a force that pulls things downward. an apple falling from a tree, a stone dropping into a pond. But in space, where there is no up or down, gravity reveals its full, majestic nature. It is not simply a force that pulls things to the ground. It is the architect of the cosmos. It sculpts galaxies, builds stars, and shapes the paths of planets. And in the story of why planets spin, gravity plays one of the leading roles. Let's return to that immense ancient cloud, the nebula. Floating gently in the emptiness of space, it seems calm. But deep within it, invisible lines of gravitational attraction are forming a vast web. Every single particle of gas and dust is being pulled by every other particle. These individual tugs are unimaginably faint, but they are relentless. Over time, millions of years, they add up. The cloud begins to collapse, not all at once and not evenly. Some areas, slightly denser than others, pull in more material, growing heavier and gaining stronger gravity. These regions become the seeds of stars and planets. The collapse starts slowly, then accelerates. Like water spiraling down a drain, the material falls inward, forming tighter and tighter spirals as it moves. And as it collapses, it spins faster. This happens because of a fundamental law of physics, the conservation of angular momentum. It's a fancy term, but its principle is beautifully simple. If an object is spinning and you reduce its size, its spin rate increases. Picture a child on a spinning merry-go-round. If the child pulls their arms in close to their body, they start spinning faster. The same thing happens to collapsing clouds of gas in space, except instead of children, we have regions billions of kilometers wide. Instead of seconds, we have spans of millions of years. As gravity pulls material inward, the original rotation of the nebula, however faint, becomes stronger, more concentrated. The cloud flattens into a disk, like dough being spun into a pizza. The center becomes hotter, denser, and more compact. This is where a star will form, igniting under the immense pressure and heat created by the collapsing material. But around this fiery core, the disk continues to spin, and within that spinning disk, other processes begin to unfold. Tiny grains of dust begin to collide and stick together, forming clumps. These clumps attract more material, growing larger and heavier. Gravity again steps in. Now, not just the gravity of the entire cloud, but the local gravity of these growing clumps. Each one becomes its own miniature gravity center, pulling in more mass from the surrounding disk. Some of these clumps will become moons, others will become asteroids, but a few will become planets. And each of these emerging planetary bodies will spin, because the material from which they formed was spinning. The cloud spun, the disk spun, the clumps spun, and so the planets spin too. But their spin isn't random, it's inherited. A cosmic heirloom passed down from one stage of creation to the next. Gravity doesn't just cause collapse, it shapes the rotation of the resulting worlds. If the original cloud was spinning slightly clockwise, then everything formed from that cloud, its star, its planets, its moons, will generally share that direction of rotation. That's why most planets in our solar system spin in the same direction, and why they orbit the sun in roughly the same plane. It's like a massive cosmic record, with planets spinning and circling in the grooves of gravity's song. But the influence of gravity doesn't end with the birth of the planets, it continues to mold them. Once a planet forms, its own gravity can affect its spin. If the mass is evenly distributed, the spin may be smooth, but if the planet has a lopsided shape, or if it undergoes massive impacts, as often happened in the chaotic early solar system, its spin can wobble, tilt, or even reverse. Some planets, like Earth, developed a stable spin, aided by the gravitational pull of their moons. Our moon helps stabilize Earth's tilt, which gives us our seasons. Without it, Earth's rotation could have been far more chaotic, tipping and wobbling unpredictably. Gravity, again, plays the quiet guardian, guiding, balancing, anchoring. It's humbling to realize that gravity, the same force that lets you feel the ground beneath your feet, is also the force that gave birth to our world. It turned dust into stone, motion into rhythm, and chaos into order. It gathered the building blocks of planets and set them spinning, each with its own speed, its own tilt, its own rhythm. And so, gravity doesn't just hold the universe together, it sets it in motion. The planets do not spin on their own. They spin because gravity made them spin, and because the universe has always been in motion. In the heart of every turning world, in the slow, graceful rotation of Saturn's rings, or the dizzying spin of Jupiter's storms, gravity's invisible hand is always at work. As you lie back and look up at the stars, you're also lying on a planet that is quietly, endlessly turning, thanks to the beautiful, tireless pull of gravity. Once the spinning cloud had collapsed into a disk, and gravity had begun its quiet work of shaping stars and worlds, the next stage of planetary creation was set into motion. What had once been a drifting sea of gas and dust was now a whirling nursery, a proto-planetary disk. And within this swirling structure, countless collisions, gatherings, and transformations began. From chaos and fragments, order and form would slowly emerge. The story of why planets spin continued here, in this great turning cradle of creation. At first, it was just dust, microscopic particles, no larger than grains of sand. These floated freely, carried by the turbulence of the disk. But even in this early stage, the laws of physics were quietly working. These tiny grains began to stick together. Not all of them, and not always, but often enough that small clusters began to grow. The collisions were soft at first, like feathers brushing together in the dark. Static electricity helped them cling. Gentle motions within the disk nudged them closer. Over time, grains turned into clumps, clumps into rocks, rocks into boulders. And all of this happened within a rotating environment. The protoplanetary disk itself was not still. It was spinning, and every particle within it carried a trace of that rotation. When grains of dust came together, their combined mass inherited the spin of the particles that formed them. As the clumps grew into larger objects, what scientists call planetesimals, they didn't just grow in size, they also developed their own spin, a slow newborn rotation imprinted by both the original spin of the disk and the tiny angular momenta of the colliding particles. Imagine holding a handful of clay and shaping it into a sphere by rolling it between your palms. As you roll, you're not only forming the shape, you're also making it spin. Something very similar was happening on a cosmic scale, except instead of hands, the forces at play were gravity, motion, and time. As these planetesimals continued to grow, they began to pull in more and more material. Their gravity became stronger. They collided with other planetesimals, and with each collision, the growing bodies absorbed more mass, and often more spin. If an object struck from the side, it could speed up or alter the planetesimal's rotation. If it hit off center, it might cause the growing object to tilt or wobble. These impacts were not gentle. In the early solar system, collisions between rocky bodies were violent, explosive, and frequent. But they were also creative. Through destruction came formation. With each impact, the new world was reshaped, its rotation adjusted like a potter's wheel being pushed from different angles. The larger a body grew, the more gravity it exerted, and the more material it attracted. Some eventually grew so large that they became fully formed planets. And with them came the spin, an echo of their chaotic beginnings. That spin could be fast or slow, tilted or straight, depending on countless variables. The angle of the collisions, the speed of the impacts, the density of the surrounding disk. No two planets formed exactly the same way, and so no two spins were alike. Jupiter, for example, the largest planet in our solar system, spins once every 10 hours, an astonishingly fast rotation for such a massive world. Its spin is thought to be a result of rapid accumulation of mass and perhaps a series of early massive impacts. Earth, meanwhile, spins once every 24 hours, a rhythm that sets the pace of our days and nights. Mars spins at a similar rate, but its spin axis is more tilted, which affects its seasons. Then there are the odd ones, Venus, which spins so slowly and in the opposite direction of most planets, and Uranus, which spins on its side, as if knocked over. These strange rotations are likely the result of huge ancient collisions with other protoplanets or rogue bodies. The early solar system was a violent place, and some impacts were powerful enough to not only reshape a world's surface, but also permanently alter its spin. But no matter how unusual or varied the spin, the cause traces back to the same source. The original motion of the dust and gas, preserved through the physics of conservation and transformed by the chaos of cosmic collisions. From the dust that stuck together to form rocks, to the rocks that merged into worlds, the rotation never truly stopped. It simply evolved. And it is this slow, steady inheritance of motion that explains why all planets spin. Spin was not added later. It wasn't the result of an external force acting on finished worlds. It was part of the very process of formation. Spin was built in, woven into the fabric of each planet's birth. When we stand on Earth and feel nothing beneath our feet, it's easy to forget that we're actually rotating at over 1,600 kilometers per hour at the equator. We don't feel it because everything around us, our oceans, our atmosphere, our bodies, is spinning with us. And yet, that motion we don't feel is one of the most ancient inheritances we carry. It connects us to the swirling nebula that gave birth to the sun and the planets, to the cosmic dust that first began to stick together in the dark. The rotation of the planets is not just a mechanical feature. It is a memory, a trace of how worlds are made. A planet's spin is like a lullaby left over from its childhood, echoing through time. And as long as the planet remains whole, as long as no force intervenes to stop it, that gentle spin continues, endlessly turning through the silence of space. As we move deeper into the story of spinning worlds, a natural question arises. If all planets are born from the same swirling disk, why do they spin so differently? Why does Jupiter rotate with astonishing speed, completing one spin in just 10 hours, while Venus takes a leisurely 243 Earth days to rotate once, and even does so in the opposite direction? The answer lies not in a single cause, but in a rich tapestry of cosmic events and delicate variables that each planet encountered during its formation. No two planets experience the exact same birth, and this is reflected in the unique way each of them spins. In the earlier stages of the solar system, everything was wild and unsettled. Imagine a room filled with thousands of spinning tops, all of different sizes, colliding, breaking apart, and reforming again and again. Each spin is affected by the last impact, the last nudge, the last change in momentum. Now expand that room into a disk billions of kilometers wide, filled not with toys, but with planetesimals, chunks of rock and ice and metal, each pulled by gravity, each moving through space with its own direction and speed. The result is a chaotic ballet where each collision is a moment of transformation. Every forming planet grew in a different part of the disk. The inner regions were hotter, filled with heavier elements and bombarded by stronger solar winds. The outer regions were colder and richer in ices and gases. These differences mattered. They determined how quickly a planet could grow, what kind of materials it would gather, and how often it might collide with other bodies. A planet that formed closer to the sun, where material was more densely packed, may have encountered more collisions in a shorter amount of time, each one altering its spin just slightly. A planet farther out might have grown more slowly, with gentler influences on its rotation. And then there were the giants, planets like Jupiter and Saturn, which formed quickly and pulled in massive amounts of gas from the surrounding disk. Their enormous gravity not only helped them grow rapidly, but also allowed them to gather momentum from vast regions of the disk. This may explain why these gas giants spin so fast. They were able to capture more angular momentum as they pulled in more and more material. Their size, combined with the rate of their formation, gave them a kind of rotational momentum that smaller, rockier planets simply couldn't match. Meanwhile, smaller terrestrial planets like Mercury and Mars had very different experiences. Mercury, being so close to the Sun, has been dramatically affected by tidal forces. These are the same kinds of forces that the Moon exerts on Earth, causing our tides. But on Mercury, the Sun's influence is far more powerful. Over time, these tidal interactions have slowed Mercury's rotation down to a strange rhythm, known as a 3-to-2 spin-orbit resonance, meaning it rotates 3 times for every 2 orbits it completes around the Sun. This is not a random quirk, but a dance that has evolved through billions of years of gravitational interaction. Mars, on the other hand, has a rotation quite similar to Earth's, with a day only slightly longer than ours. But Mars also exhibits evidence of having once had a large impact, perhaps from an object that helped tilt its axis and contributed to the creation of its 2 small moons, Phobos and Deimos. Its spin, while relatively steady now, was shaped by the chaos of its early history. And then there's Venus, perhaps the strangest case of all. Venus not only spins incredibly slowly, but it spins in the opposite direction to most of the other planets. This is known as retrograde rotation. For a long time, scientists debated how such a reversal could happen. One possibility is that Venus was struck by a massive object during its formation, an off-center collision that didn't just tilt the planet, but caused it to spin backward. Another possibility is that Venus's thick, dense atmosphere, combined with solar tidal forces, gradually altered its rotation over time. In this view, it wasn't a single catastrophic event, but a slow, invisible warping of its motion, pulled over billions of years by subtle but persistent forces. The diversity of planetary spins also reminds us that the early solar system was not a neat or predictable place. There were no set patterns, no guarantees. Every planet's spin is the result of countless tiny decisions made by the universe. The direction and angle of an impact, the density of material in a particular region, the gravitational influence of neighboring worlds. Even the presence or absence of a moon could matter. Our own moon, for example, has helped stabilize Earth's rotation, preventing wild swings in tilt that could have made our planet far less hospitable to life. Without the moon, Earth might wobble like a top near the end of its spin, causing extreme changes in climate and seasons. Planetary spin also changes over time. It is not frozen. The moon is slowly moving away from Earth, and as it does, Earth's spin is gradually slowing down. Millions of years ago, a day on Earth was only about 22 hours long. Millions of years from now, it will be longer still. This slow deceleration is driven by the same tidal forces that cause our ocean tides. Even the most ancient, seemingly permanent motions in our solar system are gently evolving, shaped by time and physics. So when we look at the planets and see their different spins, we are not seeing mistakes or exceptions. We are seeing signatures, unique cosmic fingerprints left by each world's formation. Each spin tells a story of violence and stillness, of near misses and direct hits, of invisible forces and long-forgotten collisions. The diversity of spin reminds us that every planet is not just a ball of rock or gas. It is a living memory of the solar system's earliest days. When you think about the Earth turning beneath your feet, or picture Saturn's rings whirling in the distant cold, know that these motions were shaped by ancient storms, by forgotten impacts, by the quiet, ceaseless flow of gravity and time. Each spin is different. Each one is earned, and none of them are accidental. Among the planets that orbit our Sun, most behave in a similar manner. They spin in the same direction they orbit, slowly turning like dancers circling a stage, all facing roughly the same way. But two of these planetary dancers defy the rhythm. They spin in strange ways, against the flow or sideways, as if knocked off balance or given a different script altogether. These two peculiar worlds are Venus and Uranus, and they are the rebels of the solar system. Let's begin with Venus, the planet often called Earth's twin. It's similar in size and composition, and it orbits close to our own planet. But that's where the similarities end. Venus's rotation is unlike any other in the solar system. Not only does it spin incredibly slowly, taking about 243 Earth days to complete just one turn, but it spins backwards in the opposite direction of most of the planets. If you could hover above the North Pole of Venus and watch, you would see it turning clockwise, while nearly all the others spin counterclockwise. This strange behavior is known as retrograde rotation, and it raises a puzzling question. How did Venus end up spinning this way? What could cause an entire planet to rotate in the opposite direction of the one it inherited from the spinning disk that created it? One possibility is that Venus suffered a massive impact during its early formation. In the chaos of the young solar system, collisions between planetesimals and protoplanets were common. If Venus was struck by a large enough object at just the right angle, it could have reversed the planet's spin. Not by physically flipping the planet over, but by changing the direction of its rotation. It's not an easy thing to do. Reversing a planet's spin takes an extraordinary amount of energy, but in a universe governed by violence and gravity, it's not impossible. Another theory is subtler. It doesn't involve a single massive collision, but rather the slow, relentless forces acting over billions of years. Venus has a thick, heavy atmosphere, nearly 100 times denser than Earth's. It's made mostly of carbon dioxide and clouds of sulfuric acid, and it traps heat so efficiently that the surface of Venus becomes hotter than Mercury, even though it's farther from the Sun. This dense atmosphere interacts with the Sun's gravity in a process known as atmospheric tides. Just as the Moon raises tides on Earth, the Sun exerts tidal forces on Venus's thick atmosphere. Over incredibly long periods of time, these tides may have slowly torqued the planet's rotation, dragging it backward until it reversed entirely. In this view, Venus wasn't struck violently. It was gently and continuously pulled in the opposite direction, like a wheel slowly turning against the current. Now let us turn our eyes farther out, past the asteroid belt, beyond Jupiter and Saturn, to the pale blue ice giant Uranus. From a distance it seems serene, a cold, featureless ball spinning quietly in the deep. But Uranus holds one of the greatest mysteries in planetary science. It spins on its side. Unlike the other planets, which have their spin axes tilted slightly, Earth's is about 23.5 degrees, giving us our seasons. Uranus is tilted at a staggering 98 degrees. In other words, it's almost completely horizontal. This means that for long stretches of its 84 Earth-year orbit, one hemisphere of Uranus is bathed in constant sunlight, while the other is plunged into darkness. As the planet orbits the Sun, the light shifts slowly, eventually reversing. This creates seasons that last for over 20 years at a time, bright, strange, and extreme. But how did Uranus end up in such a bizarre orientation? The leading theory again involves a colossal collision. Sometime during its formation, Uranus may have been struck by an enormous object, possibly the size of Earth or larger, that tilted the entire planet over. Unlike the impact that might have reversed Venus's spin, this one didn't just change the rotation, it knocked the entire planet sideways. The moons of Uranus and its faint ring system also orbit along this tilted plane, suggesting that whatever event occurred affected the entire system, not just the planet itself. Some scientists believe that multiple smaller impacts, rather than one gigantic blow, may have gradually shifted Uranus into its sideways position. Others have speculated that interactions with massive neighboring planets, perhaps even a now lost planet, could have gravitationally torqued Uranus over time. There is another, even more subtle theory involving the distribution of mass inside Uranus itself. If the planet's internal structure shifted over time, say, if the core became offset or the density of the outer layers changed, it could have altered the planet's axis of rotation without a dramatic impact. While this idea is less widely accepted, it reminds us that we still know very little about what lies beneath the icy clouds of Uranus. What unites Venus and Uranus is not just their unusual spins, but what those spins reveal. The early solar system was a place of chaos and surprise. These two planets are records of ancient violence, of rare and complex dynamics that broke the pattern. They are reminders that the rules of planetary formation are not rigid, but flexible, shaped by random chance, gravitational tides, and cataclysmic change. Today, Venus rotates in quiet defiance, slowly spinning backward under a smothering sky. Uranus turns sideways in the cold, distant dark, its axis pointing almost directly at the sun. Both carry the scars of their pasts, not as wounds, but as identities. Their strange spins are not errors. They are stories, cosmic memories, etched into motion. When we look at these planets through telescopes or spacecraft lenses, we're not just seeing weather patterns or glowing atmospheres. We're seeing ancient events that still shape their movement billions of years later. The slow backward turn of Venus, the sideways tumble of Uranus. They are mysteries, yes, but also messages from the past. And like all planets, they spin because the universe has never been still. Only here, in these two strange worlds, the universe whispered a different kind of motion. As planets formed from the swirling protoplanetary disk and inherited their spin, they didn't remain untouched. Over time, many of them found companions, moons. These natural satellites were not just passive observers in the sky, quietly circling their parent planets. They were, and still are, active participants in shaping the motion of the worlds they orbit. In particular, moons have had a profound and sometimes invisible influence on the spin of their planets, guiding, stabilizing, or even slowing them down over billions of years. Let's begin with our own moon, Earth's faithful companion. It may appear small when we look up at the night sky, but its effect on Earth is anything but minor. When the moon first formed, likely from the debris of a colossal impact between the young Earth and a Mars-sized body, it was much closer than it is today. The gravitational pull between Earth and the newborn moon was intense, and this created a powerful connection, one that continues to influence our planet to this day. The moon's gravity pulls on Earth's oceans, creating tides. But these tides don't just move water, they also subtly pull on the solid body of the Earth itself. This constant tugging creates friction, and friction, no matter how slight, takes energy. That energy must come from somewhere, and in this case, it comes from Earth's rotation. Over time, the moon's gravitational grip has been gradually slowing Earth's spin. Hundreds of millions of years ago, a day on Earth lasted only about 22 hours. If we look even further back, the days were even shorter. And far into the future, if nothing changes, Earth's rotation will continue to slow. But the moon doesn't just slow Earth's spin, it also stabilizes it. Without the moon, Earth's axial tilt might drift chaotically over long periods of time. This tilt, currently at about 23.5 degrees, is what gives us our seasons. With a stable tilt, the changes in season are predictable and mild enough to support a wide range of life. Without the moon, our planet could tip dramatically over time, causing extreme swings in climate, perhaps making Earth a far more hostile place. In this way, the moon acts like a gyroscope, helping to keep Earth's spin steady and predictable. Other planets with large moons experience similar effects, though not always as beneficial. Mars, for example, has two small moons, Phobos and Deimos. Unlike our moon, these tiny, irregularly shaped bodies are not big enough to stabilize Mars's tilt. As a result, Mars's axial tilt wobbles significantly over time, sometimes tilting as little as 15 degrees and other times as much as 35 degrees. These changes affect the planet's climate, potentially playing a role in the loss of its once thicker atmosphere and the disappearance of surface water. With no large moon to hold it steady, Mars is like a spinning top beginning to wobble, slowly losing its balance. Then there's Jupiter, the giant of our solar system, with at least 95 moons orbiting it. While most of these moons are small, a few are massive. Ganymede, for instance, is even larger than Mercury, but Jupiter is so massive and its spin so rapid that its moons have relatively little influence on its rotation. Instead, the story of Jupiter and its moons is one of gravitational interaction. The largest moons, Io, Europa, Ganymede, and Callisto, are locked in a complex orbital dance, a resonance that affects their internal heating and geological activity. These moons, though they do not change Jupiter's spin much, are shaped by its massive gravitational pull, and in return, shape each other's orbits. It's a reminder that in the solar system, no body is truly isolated. Everything is in motion, and everything is connected. Saturn, too, has a fascinating relationship with its moons. While its large moon Titan doesn't have quite the same effect as Earth's moon has on our planet, it still exerts a tidal pull. Interestingly, some of Saturn's smaller moons may actually be speeding up the migration of its iconic rings, redistributing material in ways that could subtly influence Saturn's rotation over very long timescales. The interplay between rings, moons, and rotation is complex and still not fully understood, but it illustrates the delicate gravitational web that exists around every planet with a satellite system. In the outer solar system, Uranus and Neptune also have moons, and their effects vary. Uranus's moons orbit along the same tilted axis as the planet itself, suggesting that whatever tipped the planet, perhaps a massive collision, also influenced the arrangement of its moons. Whether the moons have helped maintain Uranus's unusual spin, or simply adapted to it, remains a topic of research, but their presence is another piece of the puzzle. Neptune's largest moon, Triton, tells a different and dramatic story. Triton orbits Neptune in the opposite direction of the planet's spin, a retrograde orbit. This suggests that Triton was not formed around Neptune, but was captured by its gravity long ago. The process of capturing such a large object would have been violent, and it likely altered Neptune's spin in the process. Even now, Triton's backward orbit creates tidal forces that slowly drain Neptune's rotational energy. Over billions of years, this could subtly slow the planet's spin and alter its tilt. So while it may be easy to think of a planet as spinning in isolation, the truth is far more dynamic. Moons act like quiet choreographers, adjusting the rhythm of the dance, sometimes speeding it up, sometimes slowing it down, and often lending balance and grace to a performance that would otherwise wobble or falter. Even tiny moons can have cumulative effects over time. Their gravitational influence may be weak, but it is constant, and in space, consistency matters more than strength. Over millions or billions of years, Even a slight tug can have enormous consequences. Our solar system is a place where every object, no matter how small, plays a role in the greater harmony. Moons are not merely passengers, they are partners. They shape the spin of the planets they orbit, influence their climates, and in some cases, may help make life possible. So when you gaze up at the moon, or imagine the faraway moons of Saturn and Jupiter, you're not just looking at distant stones in the sky. You're witnessing guardians of rotation, keepers of rhythm, and ancient companions who have been quietly guiding their planets for eons. Their influence may be silent, but it is profound, and it continues to shape the story of spin across the solar system. In the early solar system, the space between the forming planets was anything but empty. It was crowded with fragments, planetary embryos, asteroids, icy chunks, and rocky bodies of all sizes drifting, spinning, colliding. This was an age of chaos, of endless bombardment, a cosmic demolition derby that stretched on for millions of years. And in this arena of collision and upheaval, the very nature of a planet's spin could be transformed in an instant. Collisions are among the most powerful forces that shape a planet's rotation. While the original spin of a planet is inherited from the rotating protoplanetary disk, that spin is not set in stone. It is vulnerable. It can be redirected, slowed, accelerated, or entirely overturned by a single massive impact. These colossal encounters were not just accidents. They were part of the fabric of how planets grew, merged, and evolved. Picture a young Earth still molten from its formation, spinning steadily as it grows by gathering nearby material. Then imagine a Mars-sized body hurtling toward it, an enormous mass with its own velocity, its own spin, and its own angular momentum. When this body strikes Earth, the energy released is beyond comprehension, more than enough to melt rock, vaporize oceans, and shake the very structure of a planet. But even more than that, the impact can shift the rotation of the planet itself. This is exactly what scientists believe happened to Earth around 4.5 billion years ago. The giant impact hypothesis proposes that a protoplanet named Theia collided with the early Earth in a glancing blow. The result? Not only did it throw a massive amount of material into orbit, material that would later coalesce into the Moon, but it also may have tilted Earth's axis and influenced the length and direction of its day. Earth's 24-hour rotation and its current tilt of 23.5 degrees are thought to be legacies of this ancient, violent encounter. The Earth we know today, with its balanced seasons and spinning rhythm, is a product of both creation and collision. But Earth was not alone in this experience. Nearly every planet likely suffered similar impacts in its formative years. Some of these collisions were smaller and merely nudged a planet's spin, like a paddle turning a boat slightly off course. Others were monumental, enough to completely flip a planet over or drastically slow its rotation. These are not just theoretical events. We see the evidence written across the solar system. Take Uranus, for example. Its extreme axial tilt, about 98 degrees, means it essentially rolls around the Sun on its side. This bizarre orientation is believed to be the result of a massive collision with a planet-sized body that struck it off-center. The impact would have been strong enough to knock Uranus into its current sideways spin while preserving its orbit around the Sun. The moons and ring system of Uranus, which also lie along this tilted axis, seem to confirm that the entire planet and its surroundings were affected together. Venus, too, may have been the victim of a tremendous impact. Its retrograde rotation, spinning in the opposite direction of most planets, suggests it didn't just form differently. Something dramatic must have changed its spin. Perhaps an oblique collision gradually reversed its rotation, or perhaps a series of cumulative impacts slowly altered its motion over time. Some scientists also suggest that after being struck, Venus's thick atmosphere, coupled with gravitational effects, could have completed the slow reversal. And then there's Mercury, a small, dense world that bears the scars of ancient bombardment. Its strange 3-to-2 spin-orbit resonance, where it rotates 3 times for every 2 orbits around the Sun, could be the result of both tidal interactions and a history of collisions that knocked it into an unusual rhythm. The planet's heavily cratered surface tells the story of countless impacts, each one a potential contributor to its current state. Even the gas giants, as massive as they are, were not immune. While Jupiter and Saturn spin rapidly and in the same direction as the Sun's rotation, it's possible that their early spin rates were influenced by the timing and scale of the material they absorbed, much of it arriving violently. Large impacts could have transferred angular momentum, either accelerating their spin or modifying its alignment. Though these giants are harder to read due to their lack of solid surfaces, the chaotic nature of their formation suggests that collisions were involved there as well. Beyond individual impacts, the cumulative effect of many smaller collisions must also be considered. In the swirling early solar system, a growing planet could be struck hundreds or even thousands of times by planetesimals. Each collision, however small, transferred a bit of momentum. Over time, these countless nudges added up, either reinforcing the existing spin or subtly reshaping it. Like drops of water carving a canyon, the influence of small impacts cannot be overlooked. It's also important to understand that impacts don't always affect spin in a straightforward way. The angle, speed, and size of the colliding object all matter. A head-on collision might slow a planet's spin or halt it completely. A glancing strike, especially off-center, could speed up rotation or alter the tilt of the axis, and in some cases, 2 growing planetary bodies might merge smoothly, their spins blending into a new, shared momentum. In others, the merger could be explosive, creating moons or scattering debris across the solar system. In every case, the outcome of a collision is not random. It is governed by the conservation of angular momentum, a principle that ensures motion is never lost, only transformed. When a planet is struck, the combined spins of the objects involved are redistributed. Sometimes that means a faster spin, sometimes a slower one, sometimes a spin tilted in a strange direction. And so we come to see collisions not as disruptions of planetary spin, but as creators of it. Impacts are part of the architecture of motion. They are the reason why Earth has a tilted axis and why days have their current length. They are the reason why Uranus rolls and Venus turns the wrong way. Every collision is a signature on the blueprint of a planet's identity, a cosmic brushstroke that shapes the way a world spins through space. Even today, the echoes of those ancient collisions continue. Earth's rotation is gradually slowing due to the tidal influence of the Moon, another product of a collision. The Moon itself is slowly drifting away, and the length of our days is slowly increasing. The process is imperceptible on human timescales, but it is constant. And it began with a crash. In the silence of space, collisions speak the loudest. They alter paths, build worlds, and change the very nature of time as it is measured on each spinning planet. Though we now live in a more stable solar system, the scars and spins of our planetary neighbours remind us that it was not always so. For in the beginning, to be a planet was to survive a storm of stone, and to emerge from it spinning. One of the most hauntingly beautiful questions we can ask about the nature of spinning planets is this: do they ever stop spinning? At first glance, the answer might seem simple. In the vast emptiness of space, where there is no air, no friction, and no resistance, why would anything ever stop moving? After all, if a planet is spinning and nothing is pushing against it, it should keep spinning forever, right? And in many ways, that's true. The law of conservation of angular momentum tells us that in the absence of external forces, a spinning object will keep spinning. This is one of the fundamental truths of physics, and it applies as much to planets as it does to a child's spinning top or a satellite in orbit. But space is not as empty as it seems, and planets do not exist in perfect isolation. Over incredibly long stretches of time, small forces begin to add up. Invisible hands reach out and slowly, patiently begin to tug. One of the main forces that can slow a planet's rotation is known as tidal braking. This occurs when a planet has a moon or orbits very close to a star, and the gravitational interaction between the two bodies creates internal friction. On Earth, we can see this process in action every day. The moon's gravity pulls on our oceans, creating tides, but the effect is not limited to the water. The solid Earth itself is pulled and stretched, creating a kind of internal kneading that generates heat and resistance. This process slowly robs Earth of rotational energy. Over millions of years, this steady drain causes Earth's rotation to slow. Our days grow longer, not in ways we can feel day to day, but in ways that accumulate over deep time. Hundreds of millions of years ago, a day on Earth was closer to 22 hours. In another few 100 million years, it will stretch beyond 24. The moon, in turn, is drifting slowly away from Earth as it absorbs some of the angular momentum. The spin slows, and the distance grows. It's a graceful cosmic exchange. Rotation traded for separation. But this same process can go much further. The most dramatic example of tidal braking in our solar system is the case of Mercury. Mercury is the closest planet to the Sun, and it feels the full brunt of the Sun's gravitational pull. Over billions of years, this intense interaction has brought Mercury into a state known as spin-orbit resonance. Instead of spinning freely, Mercury rotates exactly 3 times for every 2 orbits around the Sun. This strange rhythm is the result of billions of years of tidal forces working slowly, relentlessly, until Mercury's original rotation was reshaped and tamed. The Moon, too, has been caught by tidal forces. But in this case, it's Earth doing the pulling. Long ago, the Moon spun independently, turning on its axis just like Earth does. But over time, Earth's gravity created tidal bulges in the Moon's rocky body. These bulges always tried to face Earth, and the friction from this constant adjustment slowly sapped the Moon's rotational energy. Eventually, the Moon's rotation synchronized with its orbit, and it became tidally locked. Today, the same side of the Moon always faces Earth. The Moon still spins. It must, to keep the same side facing us. But it spins at exactly the right speed to match its orbital period. From our perspective, it appears still, always showing the same familiar face. This phenomenon of tidal locking is not rare. It is, in fact, incredibly common across the universe. Most moons in our solar system are tidally locked to their planets. Pluto and its moon Charon are tidally locked to each other, locked in an eternal dance where the same sides always face. And in distant solar systems, many exoplanets orbiting close to their stars are believed to be tidally locked, showing one face always to the star and one to the darkness. So, in a sense, yes, planets can stop spinning, at least in the way we normally think of it. Not in an instant, not dramatically, but slowly over billions of years. They do not freeze in place, but they fall into rhythms governed by gravity and time. Their free rotation becomes a predictable dance, controlled by the body they orbit or the moon they host. Even gas giants, though massive and spinning rapidly, may one day feel the effects of this process. Jupiter and Saturn spin quickly now, and their immense mass gives them strong momentum, but the tidal interactions with their numerous moons could slowly influence their rotation over eons. It's unlikely that these planets would become tidally locked themselves due to their enormous size, but the spin rates and internal dynamics could evolve, subtly and gradually. Beyond tidal effects, there are other forces, small, almost imperceptible, that can influence a planet's rotation. Atmospheric friction, magnetic field interactions, the gravitational tug of passing objects, and even mass redistribution within the planet itself can lead to minute changes. On Earth, the melting of glaciers and the movement of tectonic plates cause tiny variations in the planet's spin rate and the tilt of its axis. These are barely noticeable, but they serve as reminders that rotation is not as permanent as it may seem. There's also the theoretical possibility of a planet completely halting its spin, given the right conditions. If tidal braking were to continue long enough, and if the orbit and rotation were perfectly synchronized, a planet could rotate so slowly that its day would stretch to infinity. One side would burn under constant sunlight, while the other would freeze in endless night. This is not just science fiction. Some exoplanets may already exist in such states, especially those tightly hugging their stars in so-called habitable zones around red dwarfs. But even here, the story isn't entirely over. Even a planet that has stopped spinning in the traditional sense is still in motion. It still orbits its star, still feels the gravitational embrace of its neighbors, still experiences tides and pull. It may rotate more slowly than ever before, but it is not lifeless. Its stillness is not death, it is equilibrium. In the grand scale of the cosmos, nothing is truly permanent. Spin begins, evolves, slows, and sometimes becomes a different kind of motion altogether. The universe is patient, it does not hurry, and it never forgets. So when we ask whether planets can stop spinning, we are really asking about the nature of time, balance, and motion. We are asking how long a memory can last, how far a whisper of movement can travel, and how even silence can be shaped by what came before. Planets are not just objects. They are processes, slow, unfolding stories written in stone, ice, and fire. And even in their stillness, they are turning. When we look up at the night sky and imagine the planets spinning silently in the vastness of space, it's easy to see their rotation as just another mechanical fact of the cosmos. Something cold, consistent, and inevitable. But the spin of a planet is more than just a feature. It's a story. It is a fossilized trace of the past, a clue to a planet's birth, its violent youth, and the hidden forces that continue to shape it long after it has cooled. A planet's spin is not simply a rotation, it is a memory. And in studying that memory, we can catch glimpses of the earliest days of our solar system and even peer into the possible futures that lie ahead. Every rotation is a preserved moment from the dawn of time. The very first twist of a cloud of gas, the collision of ancient bodies, the formation of moons, the slow tidal drag of gravity over eons. These moments are not gone. They are recorded in motion. The speed, direction, and tilt of a planet's spin tell us about its earliest collisions, its internal structure, and the invisible gravitational dance it performs with other celestial bodies. Take Earth, for example. Our 24-hour day is not a random number. It is the result of billions of years of cosmic events. It reflects a history of spinning dust, a cataclysmic impact that birthed the moon, and the slow break applied by lunar tides. Our days were once shorter. They are slowly growing longer. Long ago, the planet spun faster. The days flew by more quickly. The moon hung larger in the sky. As the moon retreats, Earth slows, fractionally but continuously. This slowing of time is not something we can feel moment to moment, but it is happening. The Earth's rotation is a living clock, one that ticks not just forward, but also backward, toward its origins. The tilt of Earth's axis, responsible for our seasons, is another echo of ancient events. It might not seem connected to rotation at first, but it is. That tilt, stabilized by the moon, is part of Earth's spinning identity. Without it, we might not have the gentle balance of spring and fall. We might not have the slow turning of the year. Our calendars, our agriculture, and even our sense of time are linked to this ancient rotational truth. And when we look at other planets, we see other stories. Mars has a similar tilt and day length, but its small moons cannot stabilize its axis. Its rotation wobbles over time, leading to long cycles of climate variation. Perhaps part of the reason why its ancient rivers dried up and its skies thinned. Venus spins in the opposite direction, slowly, heavily, as though weighed down by the dense atmosphere it carries. Uranus spins sideways, as if toppled by an invisible hand. Each of these spins is a sentence in the autobiography of a world. By understanding why planets spin the way they do, we begin to uncover secrets that are otherwise hidden beneath layers of rock, ice, gas, and time. A planet's spin can tell us if it suffered a massive collision, if it once had a moon that is now lost, or if it has been shaped by invisible tides over ages. It can reveal whether a world is stable or chaotic, whether its climate might be predictable or wildly shifting. Even distant exoplanets orbiting stars light years away whisper hints about their nature through their rotation. Some may be tidally locked, showing one face to their sun in eternal day and hiding the other in perpetual night. Others may spin quickly, suggesting a recent formation or a thin atmosphere. Scientists are beginning to measure the rotation of these alien worlds, not by watching them directly, but by analyzing the way their atmospheres absorb light, how their brightness shifts as they rotate, and how their star's gravity distorts their orbit. From tiny wobbles and patterns in light, we extract vast stories of rotation and history. And just as spin reveals the past, it also points to the future. A planet's rotation affects its climate, its weather patterns, and its potential to host life. Rapid spin can generate strong magnetic fields, like Earth's, which shield the surface from harmful solar radiation. Slow or chaotic spin might leave a planet vulnerable to cosmic forces, stripping away its atmosphere or allowing temperatures to fluctuate wildly. In this way, spin becomes more than a historical curiosity. It becomes a factor in whether a world can remain habitable, whether it can protect and nurture life. Even human life here on Earth is synchronized to our planet's spin. Our sleep, our productivity, our mental and physical rhythms all follow the cycle of day and night, a cycle written into our biology from the moment we evolved under this spinning sky. If Earth spun faster or slower, our lives would be fundamentally different. The pace of time as we experience it is tied directly to the pace at which the planet turns. We don't often think about it, but the spin of Earth is also the reason we see stars move across the sky. The apparent motion of the heavens, sunrises, sunsets, constellations shifting overhead, is not the sky moving, but us turning. Every dawn is a rotation. Every twilight is a return. The spin of the planet creates the rhythm of our days, the unfolding of our seasons, and the poetic cycle of light and darkness. And so, the rotation of a planet is not just a number measured in hours. It is a sacred rhythm, a signature of identity, a record of history, and a quiet guide to the future. It is the heartbeat of a world. When we ask, why do planets spin? We are really asking something much deeper. We are asking how the universe began, how order rose from chaos, how ancient collisions shaped the dance of the cosmos. We are asking how the present grew from the past, and how the future will unfold. In the end, every spinning planet is a story still being written, a tale that began in a silent cloud of dust, carried forward through fire and impact, and now continues in the silent turnings we cannot feel but trust completely. And as we lie on this spinning earth, watching the stars drift overhead, we are cradled by that ancient motion. We are part of it. We are shaped by it. And we are always moving.